Hey folks, welcome back. My YouTube stream was interrupted due to this TP link network interface card, the PCIe 2.5 GBE family controller. Its driver crashed, and or it was a problem from the router itself, which prevented the streaming. So the Wi-Fi issues, the LAN issues, the network issues haven't totally been fixed yet. And I have also reported this to my sub inspector, to my local area sub inspector, the cyber cell here in Lucknow, Alambagh specifically. And yeah, I yesterday saw that some unwanted elements, uh, maybe some hackers were controlling my workstation, minimizing the running programs and manipulating the drivers of the hardware interfaces, which is happening right now. And I talked to in detail with Chandrajit, the sub inspector in the police station. And I yesterday messaged him again when someone was manipulating my drivers and messing up my installed softwares. So I will be reporting this again. This is also the reason why I'm unsure, and I tried contacting the factory security folks to come help me in the live stream, as I am sure of the prompt injections and interceptions and steering that is happening live on the stream, along with the intrusions. Since if someone has already access to the my workstation, he or she can easily get access to the Lambda workspace, the Lambda server, and might change the weights of any of the models and poison the models on which I am doing the training and other machine learning workflows. That's what I will be talking next. And let's hope this gets resolved ASAP. Anyway, this is recomputing the notebooks to compute already the outputs from a prior run, and it's taking too much time. I don't know why. Let's try running this again. Asking me for a detailed breakdown of what.
what probability should we put on, something totally out of the left field comes out and none of this is relevant?
Something that's very simple and easy to scale, I have very, very low probability for. There are a number of companies working on effectively like particle accelerators or synchrotrons that generate light that's either 13.5 nanometer like EUV or even X-ray, like even narrower wavelength, like 7 nanometer or whatever wavelengths of light to then use in lithography tools. But those things are like massive particle accelerators that are then generating this light. It's a very complicated thing to build. So there's a couple companies, and I think that could be a big disruption to the industry beyond what EUV is. I don't necessarily think that like we're going to just magically build something new that is like direct write and super simple and can be manufactured at huge volumes, although there are some attempts to do things like this.
Yeah, because I asked because if you think about Elon codes in the past, rocketry was this thing that was thought to be, I mean, it is incredibly complicated.
Look, I'm just a naive yapper compared to Elon, right? What have I built? So maybe it's possible, right?
Yeah. In order to be able to build more memory in the future, could we build 3D DRAM the way we do 3D NAND and then go back to DUV?
This is the hope. Currently, everyone's roadmap for 3D DRAM is that you'll still use EUV because you want to have that tighter overlay, because now when you're doing these subsequent processing steps, you want it to be, now everything's vertically stacked. You have more layers on top of each other. And you want the pitches to be tighter and all these things. So generally, people are still trying to do it EUV, but what 3D would do is it would take the, hey, a single EUV pass, how many bits can it make, right? If you do this sort of like calculation, and that number would go up drastically if you go to 3D DRAM. That is the hope, but right now, everyone's roadmap is sort of like you go from current, it's called a 6F cell to a 4F cell, and then finally 3D DRAM, like by the end of the decade or early next decade. So there's still like a lot of R&D and manufacturing and integration to be done. I wouldn't call that out of the cards. I think it's very much likely going to happen. It also is going to require a huge retooling of fabs, right? The breakdown of tools in a fab are very different, right? Actually, the lithography tool is the only thing that isn't like that different, but the number of them relative to different types of chemical vapor deposition or atomic layer deposition or dry etch or different kinds of etch chambers with different chemistries, all of these things, you have all these different kinds of tools for different process nodes. You can't just like convert a logic fab to a DRAM fab or vice versa back and forth, or a NAND fab to a DRAM fab in a short amount of time. And in the same way, existing DRAM fabs require a lot of retooling just to go from 1B or 1 alpha to 1 beta to 1 gamma process nodes, because now they have to add EUV and change the chemistry stacks for when you're using EUV in terms of deposition and etch, and the EUV tool has to be there. And furthermore, like when you change to 3D DRAM, there's going to be an even larger shift, and so there's a lot of retooling of these fabs that needs to happen in terms of the tools. And so that would be a big disruption. That would make EUV demand generally lower, but as we've seen across time, EUV demand as a percentage of wafer cost has trended up initially, or lithography, right? Lithography initially, I want to say in like 2014-ish era was like 16% of the wafer cost, 17%, and it's gone to 30 over the last 15 years. And for DRAM, it was in the mid-teens as well, or low teens, and now it's trended towards the high teens. And before we get to 3D DRAM, it'll likely cross into the 20% range. But then if we get to 3D DRAM, it tanks again in terms of the total end wafer cost as a percentage of EUV.
Yeah, I guess you care less about like the percent of cost and more about how much it bottlenecks.
Right, but the percentage of cost is sort of
a proxy. Yeah. So if you're Jensen or Sam Altman or whoever who stands to gain a lot from scaling up AI compute, there's these stories that they would go to TSMC and say, hey, why can't we X, Y, and Z? But I think the point you're making here is it doesn't really matter in some sense what TSMC does. And in fact, even if you have Intel and Samsung building more foundries, in the long run, you're going to be bottlenecked by ASML and other tool makers and other material makers. So first, is that correct interpretation? And second, then why should Silicon Valley people be going to the Netherlands to try to pitch ASML? Like right now, should they be trying to pitch ASML to make more tools so that like in 2030, they can have more AI compute?
It's a funny dynamic we saw in 23, 24, and 2025. People who saw the energy bottleneck before others asymmetrically went to, Siemens, Mitsubishi, and of course GE Vernova and bought up turbine capacity, and now they're able to charge excess amounts for deploying these turbines places because of energy. And in the same sense, this could be done for EUV, except ASML is not just going to trust any random bozo who wants to buy EUV tools. In the sense that these turbines are much cheaper than EUV tools, and there's many more of them produced, right? Especially once you get to industrial gas turbines or not just combined cycle, but the cheaper, smaller, et cetera, less efficient ones. People put down deposits for these. So in a sense, someone could do this, right? Someone should go to the Netherlands and be like, I'll pay you $1 billion. You give me the right to purchase 10 EUV tools 2 years from now, right? And I'm first in line 2 years from now. And then over those 2 years, you then go around and wait for everyone to realize, oh crap, I don't have enough EUV tools. And then you try and sell your option at some premium. Yeah. But all you're effectively doing is you're saying, ASML, you're dumb. You weren't making enough margin on these. I'm going to make margin. And the question is will ASML even agree to this, right? And I'm like, I don't think so, right?
So, but there's a world where they at least get a demand signal from that to increase production.
Potentially, I agree.
But it sounds like you're saying, they couldn't even increase production if they wanted to, given the
but that's exactly the market in which, if they can't increase production, just like TSMC cannot increase production that fast, and yet demand is mooning, then the obvious solution is to arbitrage this, because you and I know demand is way higher than they're projecting and their capability to build. So then you arbitrage this by locking up the capacity and then sort of doing a forward contract and then trying to sell it at a later date once other people realize, actually, shit, everything is fucked and we don't have enough capacity. And then you'll have this insane margin that ASML and TSMC should have been charging. But the thing is, I don't know if ASML and TSMC will ever agree to this.
Okay, let me ask about power now. So it sounds like you think power can be arbitrarily scaled.
Not arbitrarily, but yes.
But beyond these numbers. And I think, if I'm remembering correctly, your blog post on the power, how AI labs are increasing power, you were like, well, you were implying that GE Vernova and Mitsubishi and Siemens could produce in gas turbines was like 60 gigawatts a year. And then there's these other sources, but they're like less significant than the turbines. And so, and only a fraction of that goes to AI, I assume. So yeah, if in 2030 we have enough logic and memory to do 200 gigawatts a year, do you just think that these things are on a path to ramp up to more than 200 gigawatts a year, or what do you see?
Yeah, so I mean, right now we're at 30, right? Or 20. So this is critical IT capacity, by the way, right? This is an important thing to mention. When I'm talking about these gigawatts, I'm talking about critical IT capacity, server plugged in, that's how much power it pulls. But there's losses along the chain, right? There's loss on the transmission, there's losses on the conversion, there's losses on cooling, et cetera. And so you should gross this factor up, from 20 gigawatts for this year or 200 gigawatts by the end of the decade, to some number 20-30% higher. And then you have capacity factors, right? Turbines don't run at 100%. In fact, like if you look at PJM, which is the largest grid, I think, in America, sort of the Midwest, sort of Northeast kind of area-ish, not the full Northeast, but anyways, PJM, they rate in their models for like, hey, turbines, how much capacity? We want to have excess, roughly 20% capacity. In addition, in that 20% excess capacity, we're running all the turbines at 90% because they are derated some for reliability. Oh, things go down, maintenance, et cetera, et cetera, et cetera. So then in reality, the nameplate capacity for energy is always way higher than the actual end critical IT capacity because of all of these factors. Yeah. But it's not just turbines, right? If you were just making power from turbines, like that's simple, boring, easy, right? We're, humans and capitalism is far more effective. And so the whole point of that blog was, yes, there's only 3 people making combined cycle gas turbines, but there's so much more we can do, right? We can do aeroderivatives, right? We can take airplane engines and turn them into turbines as well. And there's even new entrants in the market, like Boom Supersonics trying to do that, right? And they're working with Crusoe. And also there's all the other ones like that already exist in the market. There's medium speed reciprocating engines, right? Engines that spin in circles, right? So sort of like any diesel engine, right? There's like 10 people who make engines that way, right? So Cummins, at least I'm from Georgia, and we people used to be like, oh man, you got a Cummins engine in there, regarding Ram trucks, but it's like, well, actually automobiles manufacturing is going down. These companies all have capacity and could scale and convert that for data center power, right? Stick all these reciprocating engines. Yes, it's not as clean as combined cycle. Maybe you can convert them from diesel to gas if you want. But at the end of the day, these spinning engines, what about ship engines, right? All of these engines for these massive cargo ships. Those are great. Nebius is doing that for a data center for Microsoft. In New Jersey, right? They're running these ship engines to generate power. Oh, there's, Bloom Energy's doing fuel cells. We've been like very positive on them for like a year and a half now, because they have like such a capability to increase their production, and their payback period for production increase is like very fast, even if the cost is a little bit higher than combined cycle, which is like the best cost and efficiency. And then there's solar plus battery, which as these cost curves continue to come down, those can come online. There's wind, and of course the derating of those, hey, when you put on a wind turbine, you might say, oh, I'm only going to expect 15% of the maximum power because things just oscillate. But yeah, batteries, there's all these things. And then the other thing is that like the grid is scaled for, hey, we are not going to cut off power at peak usage, which is like the hottest day in the summer. But in reality, that's a load spike that is 10, 15, 20% higher than the average. Well, if you just put enough utility scale batteries, or you put peaker plants that only run a small portion of the year, then all of a sudden, and those could be gas, they could be industrial gas turbines, they could be combined cycle, they could be any of the other sources of power I mentioned, they could be batteries, then all of a sudden you've unlocked 20% of the US grid for data centers, because most of the times that capacity is sitting idle and it's really only there for that peak, right? Which is a day or two. Right. And it's a few hours of like maybe a few days of the full year is that peak. And so you just have enough capacity to absorb that peak load. And all of a sudden you've transferred all. And today, data centers are only 3-4% of the power of the US grid. And by 28, they'll be 10%. But if you can just unlock 20% of the US grid like this, like it's like not that crazy. And the US grid is terawatt level, not hundreds of gigawatts level. Right. So we can add a lot more energy. It's not easy. I'm not saying it's easy. These things are going to be hard. There's a lot of hard engineering. There's a lot of risks that people have to take. There's a lot of new technologies people have to use. But Elon was the first to do this behind the meter gas. And since then, we've seen an explosion of different things that people are doing to get power. And they're not easy, but people are going to be able to do them. And the supply chains are just way more simple than chips.
Interesting. So I guess he made the point during the interview that the specific blade for the specific turbine he was looking at, the lead times for that go out beyond 2030. And your point is that
that's great. There's so many other ways to make energy.
Okay, so
like just be inefficient. Like it's fine.
Right. So you're like right now, I guess combined cycle gas turbines have capex of $1,500 per kilowatt, and you're saying it would make sense to have either technologies that are much more expensive than that, or other things that are getting cheap enough to that to make it competitive.
Exactly. Yeah. It can be as high as $3,500 per kilowatt, even, right? So it could be twice as much as the cost of combined cycle, and the total cost of the GPU, on a TCO basis has gone up a few cents per hour, right? Again, because we've been talking about Hopper pricing, $1.40 now becomes, the power price doubles. Okay, the Hopper that was $1.40 is now $1.50 in cost. Right. It's like, I don't care because the models are improving so fast that the marginal utility of them is worth way more than that 10-cent increase in energy.
Okay, and then so you're saying 20% of the grid, so 1 terawatt about, 20% of that can just come online from utility scale batteries increasing what you'd be comfortable putting on the
regulatory
grid.
mechanism there is like not easy, by the way.
But like that's 200 gigawatts, like if that hypothetically happens. But you're saying on just from the different sources of gas generation you mentioned, the different kinds of engines and turbines, combined, how many gigawatts could they unlock by the end of the decade?
Yeah, so we're tracking in some of our data where all, there's over 16 different manufacturers of power generating things just from gas alone, right? So, yes, there's only 3 turbine manufacturers for a combined cycle, but we're tracking 16 different vendors and we have all of their orders and things like that. And it turns out there is just hundreds of gigawatts of orders to various data centers. As we get to the end of the decade, we think like something like half of the capacity that's being added will be behind the meter. And when we look at like, a lot of this is actually behind the meter is almost always more expensive than grid connected, but there's just a lot of problems with getting grid connected and, permits and interconnection queues and all this sort of stuff. So it ends up being, even though it's more expensive, people are doing behind the meter, and then what they're doing behind the meter with ranges widely, right? It could be reciprocating engines, it could be ship engines, it could be aeroderivatives, it could be combined cycle, although combined cycle is not that great for behind the meter. It could be Bloom energy fuel cells, it could be solar plus battery, right? Like it could be any of these things.
You're saying any of these individually could do like tens of gigawatts?
Any of these individually will do tens of gigawatts, and in a whole, they will do hundreds of gigawatts.
Okay. So that alone should more than...
I mean, it's going to take, like electrician wages probably double or triple again, right?
Yeah.
And like, there's going to be a lot of new people entering that field, and there's going to be a ton of people who make money, but it is something that I don't see that as the main bottleneck, right?
So right now in Abilene, the 1.2 gigawatt data center that Crusoe is building for OpenAI, I think they have like 5,000 people working there, or at peak they did. And if you turn that into 100 gigawatts, and I'm sure things will get more efficient over time, but that would be like 400K people it would take to build 100 gigawatts. And if you think about the US labor force of how many electricians there are, how many construction workers there are, yeah, I guess there's like 800K electricians. I don't know if they're all substitutable in this way. There's millions of construction workers. But if we're in a world where we're adding 200 gigawatts a year, are we going to be crunched on labor eventually, or do you think that is actually not a real constraint?
So labor is a humongous constraint in this. People have to be trained. Likewise, we probably start importing the highest skilled labor in this way, right? Because now it makes sense that, hey, a really high skilled electrician in Europe who was working on destroying power plants now comes to America and is building data center, high voltage electricity, power moving across data center, right? Something like this, right? Humanoid robots maybe start to, or robotics at least start to, but the main factor is going to be for reducing the number of people is modularizing things and making them in factories in Asia. Unfortunately, but, at least for America, but, Korea, Southeast Asia, in many ways, China as well. But, these areas are going to ship more and more built out sections of the data center, and those will be shipped in, right? Maybe today you currently ship servers in or a rack in, and then you plug that into different pieces that you're shipping from different places. But now you'll ship it to a factory and integrate the entire hey, maybe this is a 2 megawatt block, and this block goes from high voltage power to the voltage power the voltage and maybe DC that you deliver to the rack instead of being AC and high voltage, right? Or something like this, right? Or cooling, you ship a fully integrated thing that has a lot of the cooling subsystems already put together. Or, because plumbers are also a big constraint here, or furthermore, you take, instead of just a single rack, and now you have people wiring up all these racks of power and electricity and blah, 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 you take a skid and you put an entire row of servers, and that is shipped from the factories. And today, a single rack may be 120, 140 kilowatts, but as we get to next generation, NVIDIA Kyber and things like that, it's almost a megawatt. And then in addition, if you do an entire row, it'll have the rack, it'll have the networking, and it'll have the cooling and the power racks all integrated together. So now when you come in, actually you have much less stuff to cable, whether it be networking with a fiber, whether it be the power, right? There's fewer power things to connect, and then there's fewer plumbing things to connect, right? And so this drastically can reduce the amount of people working in data centers, and therefore the capability to build these will be much larger. And along the way, there will be, new things mean, some people will move faster to new things, some people will move slower, right? Crusoe and Google have been talking a lot about this modularization, as has people like Meta and many others, right, have been talking a lot about this modularization, and others are going to be slower to doing it. But at the end of the day, and people who move faster to new things may have more delays, or people who are slower have labor problems. So there will always be dislocations in the market because this is a very complex supply chain. At the end of the day, it's still simple enough that we will be able to solve it through capitalism and human ingenuity on the timescales that are required.
Yeah. Okay. So speaking of big problems to solve, Elon Musk is very bullish on space GPUs. If you're right that power is not a constraint on Earth, I guess the other reason they would make sense is that even you can, there will be enough gas turbines or whatever to build it on Earth. I think Elon's next argument then is like you can't get the permitting to build hundreds of gigawatts on Earth. Do you buy that argument?
Land-wise, it's pretty. America's big. Data centers don't take that much space. Yeah. You can solve that. permitting wise, air pollution permits are a challenge, but the Trump administration's made it much easier. You go to Texas and you can skip a lot of this red tape. And so, Elon had to deal with a lot of like this complex stuff in Memphis and then building a power plant across the border and all these things for Colossus 1 and 2. But at the end of the day, there's a lot more you can get away with in the middle of Texas, right?
But why, given that Elon lives in Texas, why didn't he just go to Texas?
I think it was partially like they over-indexed on grid power for a temporary period of time, right? Because that's just what they thought they needed more of.
Because they had an aluminum refinery connected to the grid there.
It was an appliance factory that was idled. But I think they may have indexed more to what was grid power. They may have indexed more to like water access and gas access because actually I think they bought that knowing that the gas line was right there and they were going to tap it. Same with water. It was a whole host of different constraints. It was probably an area where electricians and things like that were easier to find. But at the end of the day, I'm not exactly sure why they chose that site. I bet Elon would have chosen somewhere in Texas if he could have like gone back. But because of the regulatory challenges he's faced, it's ultimately like permitting is a challenge, but America is a big place and there are 50 states and things will get done. And there are a lot of small jurisdictions where you can just transport in all of the workers that you need for a temporary period of 6 months to a year, depending on the type of contractor. It can be even 3 months depending on the type of contractor that's coming in, and put them in temporary housing, pay out the butt because labor is very cheap relative to the GPUs and the power, or not the power, but the GPUs and the networking and so on and so forth. And the who do these RMAs and such.
What do you make of Elon's kind of argument that once you have the initial, after an initial phase, they actually don't feel that much?
Sure, but now you've done this, you've tested them all, you deconstructed them, put them on a spaceship, fucking put them into space, and then put them online again. That's months, right? And if your argument is that, hey, GPUs have a useful life of X years, right? If a GPU has a useful life of 5 years and it takes 3 additional months, probably 6, let's say 6 additional months, then that is 10% of your cluster's useful life.
Yeah.
And because we're so
So
I
much
mean,
effort.
networking these chips together is a problem, and you can't just make the satellite infinitely large, right? Like there are a lot of challenges with physics to making a satellite really big, right? So then that's why you need these
Right.
interconnects between the satellites. Those interconnects are more expensive than a cluster, like 20% of the cost or 15% of the cost is networking. All of a sudden, now you're making it like space lasers instead of like pretty simple like lasers that are manufactured in millions of volumes with, pluggable transceivers. And those things are very unreliable as well. More unreliable than the GPUs, by the way. Across the life of a cluster, you have to unplug, clean it all the time, right? Unplug, replug it just for random reasons. These things are just not as reliable. So you've got that problem as well. Like you've got a more expensive, complicated space laser to communicate instead of this pluggable optical transceiver that's been in super high volume.
Okay, so all in all, what does that imply for space data centers?
So space data centers effectively are not limited by, hey, we have this energy advantage. It's actually just limited by the same contended resource. We can only make 200 gigawatts of chips a year by the end of the decade. So what are we going to do to get that capacity? It doesn't matter if it's on land or in space. It doesn't really matter, right? Because you can build that power. And I think human capabilities and capacity could get to the period where we're adding a terawatt a year globally of various types of power. At some point, we do cross the chasm where space data centers make sense, but it's not this decade, right? It is much further out once you have energy constraints actually being a big bottleneck, once you have space, land permitting be a much bigger bottleneck as it subsumes more and more of the economy, and chips are no longer the bottleneck because chips are the biggest bottleneck. And so you want them deployed working on AI the moment they're done being manufactured. And so there's a lot of things people are doing to increase that speed faster and faster, whether it be modularizing data centers or even modularizing racks where you actually put the chip in at the data center, but only the chip and everything else is already wired up and ready to go at the data center. So there's things like this that people are doing to decrease that time that you cannot do in space. And at the end of the day, all that matters in a chip-constrained world is get these chips working on producing tokens ASAP in a world, maybe 2035, once the semiconductor industry and ASML and Zeiss and all these other suppliers, Lam Research Applied, materials, fab manufacturers, like pendulum swings and they're able to make enough chips. And really, we're optimizing every dial. And like it makes sense to optimize the 10% of energy costs or 15% of energy costs, or as we move to ASICs potentially, and NVIDIA's margins aren't 70+%. Maybe that energy cost is 30% of the cluster, and fab construction, all this. Like these are the things, or data center construction, these are the things to optimize. But that's not Elon doesn't win by doing, 20% gains. Elon never wins that way. Elon wins when he swings for the fences and does 10x gains. Right? That's what SpaceX is about. That's what Tesla was about. That's what all of his success has been about, right? It's not been about these chasing the 20%. So I think space data centers will eventually be a 10x gain, potentially as Earth's resources get more and more contentious. But that's not this decade.
Yeah. I mean, I think just to drive some intuition about how much land there is on Earth, obviously the chips themselves, especially if we move to a world where you have racks that have megawatts, megawatt charge, like literally, it's not even a Rhino factor.
That's the other thing, right? The power density, if chips and manufacturing is the constraint, right now, roughly it's 1 watt per millimeter squared for AI chips and such. One easy way is to pump that to 2 watts per millimeter squared. Now, you may not get 2x the performance. You may only get 20% more performance, and that requires much more exotic cooling, right? It requires more complicated cold plates and very complicated liquid cooling, or maybe it requires like things like Emergent cooling. But in space, higher watts per millimeter is very difficult, whereas on Earth, these are solved problems. And one of these things enables you to get a lot more tokens. Maybe it's 20% more tokens per wafer that's manufactured. And that's a humongous win.
Square millimeter, you mean of die area?
Yeah, of die area. Square millimeters of a die area.
I mean, it would be better for space because if you can run more watts per millimeter would be the chip runs hotter, and the hotter the chip. I guess it's a question of computer chip engineering, but it cools to the power of 4th by Stefan Boltzmann's law. So if you can run a very hot chip because it allows water to go
you can't run it hotter. You can only run it denser. And the problem is getting the heat out of that dense area means you have to move away from standard air cooling and liquid cooling to more exotic forms of liquid cooling or even immersion to get to higher power densities. And that's more difficult in space than it is on Earth.
Yeah. And maybe it's at this point worth explaining what exactly a scale-up is and what it looks like for NVIDIA versus Trainium versus TPUs.
Yeah, so earlier I was mentioning how communication within a chip is super fast.
Yeah.
Communication within chips that are in the same rack is fast, but it's not as fast. And then, it's on the order of terabytes. And then communication very far away is on the order of hundreds of gigabytes, right? So this order of magnitude as you get further distance compute, and maybe across the country, it's on the order of gigabytes a second, right? Scale-up domain is this like tight domain where the chips are communicating on the order of terabytes a second. And so for NVIDIA, previously, this meant an H100 server had 8 GPUs, and those 8 GPUs could talk to each other at terabytes a second. With Blackwell, NVL72, they implemented rack scale up. And that meant all 72 GPUs in the rack could connect to each other at terabytes a second speed. And the speed doubled gen on gen, but also the most important innovation they did was going from 8 to 72 in the domain. When we look at Google, their scale-up domain is completely different, right? It has always been on the order of thousands, right? With TPU v4, they had pods the size of 4,000 chips. With V8, they have pods even, or V7, they have pods in the 8,000, 9,000 range. And what's relevant here is that it's not the same as NVIDIA. It's not like for like. Google has a topology that's a torus, right? So every chip connects to 6 neighbors. Rather than NVIDIA, the 72 GPUs connect all to all, right? So they can send terabytes a second to each other, to any arbitrary other chip in that pod of scale up. Whereas Google, you have to bounce through chips, right? So this means if TPU 1 needs to talk to TPU 76, then it has to bounce through various chips. And there is always some blocking of resources when you do that. So because that one TPU is only connected to 6 other TPUs. And so there's a difference in topology and bandwidth, and there are trade-offs and advantages of both, right? Google gets to have a massive scale-up domain, but then they have the trade-off of you have to bounce across chips to get to from one chip to another. You can only talk to 6 direct neighbors. And so there is like this trade-off. And Amazon, it has mutated their scale-up domain. They're somewhere in between NVIDIA and Google effectively, where they're trying to make larger scale-up domains. They try and do all-to-all to some extent, which is what with switches, which is what NVIDIA does, but also to some extent they use torus topologies like Google does. And as we advance forward to next generations, all 3 of them are moving more and more towards a dragonfly topology, which means there's sort of like there is some fully connected elements and there's some elements that are not fully connected. Yep. So you can get the scale up to be hundreds or thousands of chips, but also have it not contend for resources when you're bouncing through chips.
Related question. I heard somebody make the claim that the reason the parameter scaling has been slow and only now are we getting bigger and bigger models from OpenAI and Anthropic is that so original GPT-4 is over 1 trillion parameters, and only now are models starting to approach that again. And I heard a theory that the reason is that NVIDIA's scale-ups have just not had that much memory capacity. And so, what was the claim exactly? If you have, say, let's say you have a 5T model running at FP8, so that's 5 trillion gigabytes.
Yeah.
And then you have the KV cache, let's say it's like...
Just call it the same size.
Let's say it's the same size for one batch. So you need 10 terabytes to be able to run
a single forward pass, yeah.
And then only with the GB200 and VL72 do you have an NVIDIA scale up that has 20 terabytes. And before that, they were much smaller. Whereas Google, on the other hand, has had these huge TPU pods that are not all to all, but still have, I think, hundreds of terabytes of capacity in a single scale up. So does that explain why parameter scaling has been slow?
I think it's partially the capacity and bandwidth, but also as you build a larger model, the ability to deploy it is slower, right? Like in terms of like, hey, what is the inference speed for the end user? That's kind of irrelevant. What's really relevant is RL. And what we've seen with these models and allocation of compute at a lab is sort of there's a few main ways you can allocate compute. You can allocate it to inference, i.e. revenue. You can allocate it to development, i.e. making the next model, and you can allocate it to research. And in development specifically, you split it between pre-training and RL, right? And so when you think about, hey, what exactly is happening? Well, the compute efficiency gains you get from research are so large, you actually want most of your compute to go to research, not to development. Because, all these researchers are generating new ideas, trying them out, testing them, and continuing to march along this and push the Pareto optimal curve of scaling laws further and further and further. And at least what we've seen empirically is like model cost gets 10x cheaper every year, or even more than that. Which at the same scale it gets 10x cheaper, or to reach new frontiers, it costs the same amount or more, right? So you don't want to allocate too many resources to pre-training and post and RL. You actually want to allocate most of your resources to research. And then in the middle is this like development period. If you pre-train a 5 trillion parameter model, now you have to spend all this time. How many rollouts do you have to do in these RLs? And these rollouts for a trillion parameter model versus a 5 trillion parameter model are 5 times larger, which then means it takes, if you wanted to do as many rollouts, maybe the larger model is more sample efficient. Let's say it's 2x more sample efficient. Okay, great. Now you need 2.5x much time of RL to get the model smarter. Or you could RL the smaller model for 2x the time, and you'd still have a 50%, or you'd still have a 25% difference in the big model, which is 2x more sample efficient, and doing X number of rollouts versus the small model, which is a trillion parameters, although it's less sample efficient, is doing twice as many rollouts. It's still done faster. And so you get the model faster, sooner, and you've done more RL, and then you can take that model to help you build the next models, help your engineers train and do all these research ideas. And so this feedback loop is actually weighed towards smaller models. In every case, no matter what your hardware is. And then as you look to Google does deploy the largest production model of any of the major labs, right? With Gemini Pro. It is a larger model than GPT 5.4. It's a larger model than Opus. And so you end up with, yes, Google does this because they have a unipolar set of compute, right? Almost all TPU. Whereas Anthropic is dealing with H100s, H200s, Blackwell, Trainiums, TPUs of various generations, right? And OpenAI is dealing with mostly NVIDIA right now, but going towards having AMD and Trainium as well. The fleets of compute, like Google can just optimize around a larger model, and they can leverage 1,000 chips in a scale-up domain to get, the RL time speed much faster, so that you can actually have this feedback loop be fast. But at the end of the day, in isolation, you almost always want to go with a smaller model that gets RL'd faster. and gets deployed into research and development.
Right.
So you can build the next thing and get more compute efficiency wins. And then this compounding effect of, oh, I made a smaller model that I RL'd more, that I then deployed into research and development earlier, and I spent less compute on the training itself because I was able to allocate more compute to the research. This like compounding effect of being able to do the research faster and faster and faster is potentially a faster takeoff. And that's all these companies want, is fastest takeoff possible.
Yeah. Okay, spicy question. You're explaining, you make the semi-analysis sells these spreadsheets, and you're always like, 6 months ago or a year ago, we told people the memory crunch, or now you're telling people the clean room crunch, and then in the future, the tool crunch. Why is Leopold the only person that is using your spreadsheets to make outrageous money? What is everybody else doing?
I think there are a lot of people making money in
Move do.md to mechanistic underscore analysis slash paper folder, in which you have all the other MD files, and update do.md and paperback.md with all the results from notebooks 1 to 8 with the hypothesis and interpretation guidelines reflecting the empirical numbers as well as the theoretical properties and the patterns that have been observed across the notebooks, across all the notebooks from 00 underscore to 07 underscore.
On the entire like about the AGI takeoff though, right?
Right. I mean, but the bets are not about like what happens in 2035. The bets that you're making, that are at least exemplified by public returns we can see for different funds, including Leopold's, are about what is happening in the last year. And the last year stuff could be predicted using your spreadsheets, right? So it's less about, it's about buying like the next year spreadsheets.
They're not just spreadsheets. There's reports. There's API access to the data. There's a lot of data. But anyways, I think.
But do you see what I mean? Like it's not about some crazy singularity thing. It's about like, do you buy the memory crunch?
A simple one though is like you only buy the memory crunch if you believe AI is going to take off in a huge way. And the memory crunch, a lot of it was predicated on like, at least for like people in the Bay Area who think about infrastructure, it's like obvious. KV cache explodes as context lenses get longer, so you need more memory. And then you do the math, and you also have to have a lot of supply chain understanding of like what fabs are being built and what data centers are being built and how many chips and all these things. And so we track all these different data sets like very tightly. But at the end of the day, it takes, someone to fully believe that this is going to happen. Like I think a year ago, if you told someone memory prices were quadruple and smartphone volumes are going to go down 40%, over the year or two after that, people were like, you're crazy. That never happened. Except a few people do believe that, and those people did trade memory, right? And people did. I don't think like Leopold was the only person buying like memory companies. I think there were a lot of people buying memory companies. He of course sized and positioned and did things in better ways than some, maybe most, right? I don't want to comment on whose returns are what, but he certainly did well. But other people also did really well, right? You're trying to be like this. Wow, you've made me diplomatic for the first time ever. No, you're fine. I think it's hilarious, right? I'm being a diplomat, whereas usually I'm like spicy.
Yeah. Okay. Maybe some rapid fire to close out. Can TSMC, if you're saying, look, the memory logic, et cetera, the N3 is mostly going to be AI accelerators, but then there's N2, which is mostly Apple now, and then in the future, I guess AI would also want to go on N2. Can they kick out Apple if NVIDIA and Amazon and Google say, hey, we're willing to pay a lot of money for N2 capacity?
So I think the challenge with this is chip design timelines take a long while. And so that's more than a year. And the designs that are on 2 nanometer are more than a year out.
Yeah.
And so what would really happen is NVIDIA and all these others will be like, hey, we're going to prepay for the capacity and you're going to expand it for us. And then Apple would be, and maybe TSMC takes a little bit of margin, but not a ton. They're not going to kick Apple out entirely, right? What they're going to do is when Apple orders X, they may say, hey, we project you only need Y or X minus 1. And so that's what we're going to give you is X minus 1. And then that flex capacity Apple's kind of screwed on. Whereas traditionally, Apple's always over-ordered by like 10% and cut back by 10% over the course of the year. And some years they hit the entire 10%, just, volumes vary, right? Based on the season and macro, blah, 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 blah. And so I don't think TSMC would kick out Apple. I think Apple will become a smaller and smaller and smaller percentage of TSMC's revenue and therefore be less relevant for TSMC to cater to their demands. And TSMC could eventually start saying, hey, you got to pre-book your capacity for next year for 2 years out and you have to prepay for the CapEx because that's what NVIDIA and Amazon and Google are doing.
Yeah, I wonder if it's worth going to specific numbers on like I don't have any of them on hand of like how many N2 wafers what percentage of N2 does Apple have its hands on versus over the coming years versus AI?
Yeah, I mean, this year Apple has the majority of N2 that's going to get fabricated. There's a little bit from AMD. They are trying to make some AI chips and CPU chips early. There's a little bit, but for the most part, it's Apple. And as we go forward to the year after that, Apple still gets closer to like half of it as other people start ramping. But then it falls drastically, right? Just like for N3, they were half. We'll see. And when I say N2, that includes A16, which is a variant of N2. Over time, those nodes will be the majority. And what's also interesting is traditionally Apple's been the first to a process node. 2 nanometers is actually the first time they're not. Well, besides Huawei, right? Huawei back in 2020 and before was the first with Apple, but they were both making smartphones. Now with 2 nanometer, you've got AMD trying to make a CPU and a GPU chiplet that they used advanced packaging to package together in the same time frame as Apple. And this is a big risk for AMD that causes potential delays, potentially, because it's a brand new process technology. It's hard. But at the end of the day, this is a bet that they want to do to scale faster than NVIDIA and try and beat them. As we move forward, actually, when we move to the A16 node, the first customer there is not even Apple. It's AI. And as we move forward, that will become more and more prevalent. Not only will Apple not be the first to a node, they will also not be the majority of the volume to the new node. And then they'll just be like any old customer. And because the scale of TSMC's CapEx keeps ballooning, but Apple's business is kind of not growing at the same pace, they become a less and less relevant customer. And they also will just cut their orders because things in the supply chain are kicking them out, whether it be packaging or materials or DRAM or NAND. These things are increasing in cost. They can't pass on all the cost to customers likely because the consumer is not that strong. And you end up with like this conundrum where they are just not TSMC's best bud like they have been historically.
Do you think if Huawei had access to 3 nanometer, they would have a better accelerator than Rubin?
Potentially, yeah. I think Huawei, they were the first with a 7 nanometer AI chip as well. They were the first with a 5 nanometer mobile chip, but they were the first with a 7 nanometer AI chip. The Huawei Ascend was like 2 months before the TPU and like 4 months before NVIDIA's, I want to say, was it V100 or A100? A100, I think. Yeah. And so, I mean, that's just moving to a process node. That doesn't imply software, it doesn't imply hardware design, all these other things. But Huawei is arguably the only company in the world that has all the legs, right? Huawei has cracked software engineers. Huawei has cracked networking technologies. That's, in fact, their biggest business historically, right? And they have cracked AI talent. But furthermore, beyond NVIDIA, they actually have better AI researchers. And furthermore, beyond NVIDIA, they have their own fabs. And furthermore, beyond NVIDIA, they have, their own, end market of like selling tokens and things like that. And Huawei tends to be like, they're able to get the top talent. NVIDIA is as well, but not as in much concentration. And Huawei has a bigger pool in China. It's very arguable that Huawei, if they had TSMC, would be better than NVIDIA. And there are areas where China has advantages outside of, in areas that NVIDIA can't access as easily, right? Around not just scale, but also like some things around, certain optical technologies. China's.
If humanoids take off faster than people expect, if by 2030, there's millions of humanoids running around, which each need local compute. Any thoughts on what that implies? What will be required for that?
There's a lot of like difficulties with like the VLMs and all these things that VLAs that people are deploying on robots. But to some extent, you don't need to have all the intelligence in the robot. And it would be much more efficient to not do that, right? Because in the server, in cloud, you can batch process and all these things. So what you may want to do is, hey, a lot of the planning and longer horizon tasks are determined by a much more capable model in the cloud that runs at very high batch sizes. And then it pushes those directions to the robots who then interpolate between each subsequent action or is given like, hey, pick up that cup. And then the model on the robot can pick up the cup. And it's like, as it's picking up, it's like, oh, in fact, this, things like weight and all these things might have to be, and like force may have to be like determined by the model on the robot, but not everything needs to be like, hey, pick up the robot, this, right? Or like, hey, that's a headphone. Actually, I'm the supermodel in the cloud. I know that this headphones are, Sony XM6s, which is not a Dwarkesh ad spot, but
I'm like, why is this guy plugging this thing so hard? It's like on the table. It's like on his neck when we're entering Satya together. Like, is he getting paid by Sony?
Unfortunately not. Unfortunately not. But anyways, like, it might say, hey, the headband is soft and this is this is the weight of it and all these things. And then the model on the robot can be less intelligent and take these inputs and do the actions. And it may get told by the model in the cloud every second, every 10 times a second, maybe, it depends on the hertz of the action, but a lot of that can be offloaded to the cloud because otherwise, if you do all of the processing on the device, I believe it would be more expensive because you can't batch. 2, you couldn't have as much intelligence as you do in the cloud because the models will just be bigger in the cloud. And 3, we're in a semiconductor shortage world and any robot you deploy needs leading edge chips because the power is really bad for robots, right? You need it to be low power and efficient. And all of a sudden you're taking power and chips that would have been for AI data centers and you're putting them in robots.
Yeah.
So now that 200 gigawatts gets lower if you're deploying millions of humanoids.
I think this is very interesting because something people might not appreciate about the future is how centralized in a physical sense intelligence will be. Where right now with humans, your compute, like there's 8 billion humans and their compute is on their heads, on their person. And in the future, even with robots that are out physically in the world, I mean, obviously knowledge work will be done in a centralized way from data centers with huge, like maybe hundreds of thousands of instances or maybe millions of instances. But even for robotics, the future you're suggesting is one where there's like more centralized thinking and centralized computation that's driving, millions of robots out in the world. And so I think that's just like, that's an interesting fact about the future that I think people might not appreciate.
I think Elon recognizes this, which is why he's like going to different places for his chips, right? He signed this massive deal with Samsung to make his robot chips in Texas because he thinks, I personally think he thinks that, Taiwan risk is huge. And because of that and the centralization of resources in Taiwan, him having his robot chips in Texas and also being a separate supply chain that is not as constrained by, no one's making AI chips really on Samsung besides NVIDIA's new LPU that they're launched. They're launching it next week, but we're recording it the week before.
It's coming out this week. This episode's coming out Friday.
Oh, this episode's coming out before. Sick.
Yeah.
So they're launching this new AI chip next week which is built on Samsung, but that's like sort of a recent development from NVIDIA. And then that's the only other AI demand there, whereas on TSMC, everything is competing. So he gets this like both geopolitical diversification, but also the supply chain diversity for his robots. And he's not as competing as much with the like willingness to pay of infinity of the data center of geniuses.
Okay, final question. On Taiwan, if we believe that tools are the ultimate bottleneck, how much of Taiwan's place in the AI semiconductor supply chain could we de-risk simply by having a plan to airlift every single process engineer at TSMC out when things come to, if they get blockaded or something? Or do you actually still need to ship out the EUV tools, which would be multiple plane loads per single tool and would not be practical?
If you ship out all the process engineers, and assuming it's like hot enough that you destroy the fabs, no one has all the fabs in Taiwan now, which is a big risk, right?
Yeah.
These tools actually use a lot of semiconductors, which are manufactured in Taiwan. So it's like a snake eating its own tail sort of like meme, because you can't make the tools without the chips from Taiwan, which you can't use without the tools in Taiwan. There's obviously some diversification there, but and they don't use super advanced chips in lithography tools. But at the end of the day, there is some tail eating the dragon. Just shipping out all the engineers and blowing up the fabs means China has a stronger semiconductor supply chain than the rest of the world, right? In terms of verticalization, now that you've removed Taiwan. And now you've got all the know-how, but you've got to replicate it in, let's say, Arizona or wherever for TSMC. And it's going to take a long time to build all the capacity that TSMC had built over the years. And so you've drastically slowed US and global GDP, not just growth, you've shrank the GDP massively. And you've got a lot bigger problems, and your incremental ability to add compute goes to almost zero, right? Instead of hundreds of gigawatts a year by the end of the decade, let's say by the end of the decade something happens to Taiwan, now you're at maybe like 10 gigawatts across Intel and Samsung, or 20 gigawatts. It's like nothing.
Right.
But now all of a sudden you've like really caused some crazy dynamics in AI. Of course, you have all the existing capacity, but that existing capacity pales in comparison to the capacity that's being expanded.
Yeah. Okay, Dylan, that was excellent. Thank you so much for coming on the podcast.
Thank you for having me, and see you tonight.
Yes.
There are a couple of problems in this 08_cross_lingual